Hey everybody, my name is Chris and I'm a tutor here at Chegg.com. I mainly do math and computer science, and in this video I'd like to do an example of using DeMoivre's theorem to simplify an expression. So here we have to simplify the quantity here, 1 plus I times the square root of 3, all raised to the 6th. And here we're talking about I as the imaginary unit, the square root of -1. So sort of dealing with complex numbers here. Okay, so there are actually a couple different ways to approach this, at least. So one way is to just directly evaluate 1 plus I root of 3 times 1 plus I root of 3 6 times like that. And that is going to be terrible, just absolutely totally awful. So we don't want to do that. But what we do want to do is use DeMoivre's theorem, because that's going to greatly simplify this calculation. So first, let's go ahead and clear some room here for ourselves. And let's see what DeMoivre's theorem actually says, and then we'll talk about how we can use it in this context. So, if we go to page 2 here, we see that DeMoivre's theorem says the cosine of theta plus I times the sine of theta, all that raised to the nth power, is equal to the cosine of n times theta plus I times the sine of n theta. So this theorem might not really look like much, but it's actually incredibly powerful and useful, and the fact that it's true is just so amazing. It's one of the better examples, I think, of how complex numbers are really useful in simplifying things that are otherwise tremendously difficult. So let's go ahead and see how we can use that here. So we see that we have to have something in the form cosine theta plus I sine theta being raised to the nth power here. And you might look at this and say, oh, well, okay, here's our cosine theta, here's our sine theta, and then here's our n. Now, we can't quite do it like that. We have to be very careful. What we have to do first is convert this into something that's that we can express in terms of cosine and sine, and we can't just do that right away. So first what we have to do is identify x and y. So here's our x, 1, and then here's our y, positive square root of 3, because we have a plus sign here. So everything's positive, so that's good. Nothing to worry about there. And then this is our n, that's okay. N is 6. So we have x equals 1, and y equals the square root of 3. So we have to identify theta. How are we going to get theta? Well, because x and y are both positive, we can just use the formula theta equals the inverse tangent, so tangent inverse, of y over x. Now, if x and y were not both positive, if one of them was negative, or if they were both negative, we'd have to do something a little bit different. But I don't want to get too much into those details because we don't want to make this any more complicated than it really has to be. So because x and y are both positive, we can just use this formula. Theta is the inverse tangent of y divided by x, which in this case is the inverse tangent of square root of 3 divided by 1. So y divided by x is root of 3 divided by 1, which is just the square root of 3. So we want to take the inverse tangent of the square root of 3. Now, at this point, it's really just a matter of knowing your unit circle, which I highly recommend knowing, and the answer for that's going to be pi over 3. So the inverse tangent of the square root of 3 is pi over 3, so that's our theta. Okay? Now, we're not quite there yet. There's one more thing we have to do. We have to find the radius. So what we're really doing here is converting this complex number, 1 plus I root 3, we're converting it into polar form. So right here, it's in rectangular form, because we have the rectangular coordinates x and y, where x is 1 and y is the square root of 3, and we want to convert it to polar. And for polar form, we need r and theta. Okay, so for rectangular, we have x and y, and for polar, we need r and theta. And we just found theta. Okay, theta is pi over 3. Now we have to get r. What's r? Well, r is the positive square root of x squared plus y squared. Now, in this case, x is just 1, so x squared is just 1, so we have the square root of 1 plus y is the square root of 3, so y squared is just 3. 1 plus 3 is 4, so we have the square root of 4, which is just 2. Okay, so that's great. So r is 2, and theta is pi over 3. So in polar form, this number is 2 times cosine of pi over 3 plus I sine pi over 3. Okay, so again, 1 plus I times the square root of 3, that's a complex number in rectangular form, and before we can use DeMoivre's theorem, we have to convert to polar form with r's and thetas. So here we have 2 times the whole quantity cosine pi over 3 plus I times the sine of pi over 3. And this r right here is actually why in the beginning we couldn't just say, oh, here's cosine of theta and here's sine of theta. Okay, so remember in the very beginning we mentioned that we weren't just able to do that. Okay, so we have cosine theta here plus I times the sine of theta, and we said we can't just say here's cosine, here's sine. And the reason is because of this r right here. Okay, so we have to be very careful about that. Make sure we convert to polar coordinates the proper way, and then we could use DeMoivre's theorem. So how do we use it now? Well, let's go ahead and go to page 3. So we want to evaluate 1 plus I times the square root of 3, all of that raised to the 6th power. And we have just seen that 1 plus I times the square root of 3 equals 2 times cosine of pi over 3 plus I times the sine of pi over 3. Well, therefore, 1 plus I root 3 all raised to the 6th is going to be this entire thing all raised to the 6th. Okay? So, because we have 2 multiplied by this entire thing separately, then what we can say is this is 2 to the 6th. 2 to the 6th times cosine of pi over 3 plus I times the sine of pi over 3, all raised to the 6th. That's a plus sign right here. So now we can evaluate separately 2 to the 6th and this piece right here. So what's 2 to the 6th? Well, 2 to the 6th is going to be 64. So if you're not sure about that, you can just multiply 2 by itself 6 times, which is significantly easier than multiplying this by itself 6 times. So 2 to the 6th is 64. Now, what about this guy right here? What about this? Well, notice this is exactly in the form that we need it to be in, so that we can use DeMoivre's theorem. So DeMoivre's theorem says cosine of theta plus I sine theta all raised to the n equals cosine n theta plus I sine n theta. Well, we have exactly that right here with theta as pi over 3, okay, and n is 6. So DeMoivre's theorem tells us that that thing right there equals cosine of n theta, which is 6, times pi over 3, and then plus I times the sine of n theta, which again is just 6 times pi over 3. Okay, so again, all we did was just use DeMoivre's theorem here with theta as pi over 3 and n is 6, because this is exactly what we had here, exactly in the form that we need it to be. Okay, so now we just simplify. So we still have 64 out here. And now 6 pi over 3 simplifies to 2 pi, so we have cosine of 2 pi, and then plus I times the sine of 2 pi again. So now from here, again, it's just a matter of knowing the unit circle. So cosine of 2 pi, if we know our unit circle, cosine of 2 pi is just 1, and the sine of 2 pi is just 0. So what we end up with is 64 times 1 plus 0 times I, or in other words, 64 times 1, which is just 64. Okay, so that's the final answer, which is also pretty amazing, I think, that we can take something like this, 1 plus I times the square root of 3. So we have something complex, we have this irrational piece right here, the square root of 3, and we raise it to the 6th power. 6 is a relatively nice number, and we end up with this really nice number, 64. That to me is just incredible that something like that could actually happen. But that really just shows you the power of complex numbers in DeMoivre's theorem here. So again, this is an example of using DeMoivre's theorem to simplify something in a much easier way than it would be had we done it directly. So 1 plus I times the square root of 3 all raised to the 6th, and we get 64. So I hope you found this video helpful, and thank you for watching.